In this module, we discuss in detail the most widely used distribution for computing probabilities and inferential statistics, namely the Z distribution. You shall learn here why do we transform every normal distribution into a Z distribution. What are the properties of Z distribution? How to compare probabilities and percentiles using Z distribution. Common applications of Z distribution to sampling distribution of sample, means and sample totals. The normal distribution is the most extensively used continuous distribution. Many real-life phenomena such as distribution of marks, height and weight of the students, distance, heights of ocean waves and many behavioral events are found to be normally or near normally distributed. Even the sample means and sample totals are normally distributed even if the sampled population is non-normal. Many procedures of inferential statistics are also based on the assumption that the underlying data is somewhat normally distributed. However, on account of its computational difficulties in finding probabilities or areas and to make comparisons between distributions having different units of measurement, we need to transform them in some ways. By converting normally distributed random variable into Z variable, we transform the data into a standard normal distribution. It is a special case of normal distribution, the distribution that occurs when a normal random variable has a zero mean and standard deviation of 1. With this conversion, we can determine probabilities for any normal distribution using the standard normal tables. Z distribution. Let us begin this module by briefly recollecting the meaning and properties of the normal distribution, which you have already learned in the earlier module. Properties of the normal distribution. A continuous random variable x is said to have a normal distribution if its probability density function is given by the following equation. Fx is equal to fx mu sigma square, which is equal to 1 upon sigma into square root of 2 pi into e raised to power 1 upon 2 into x minus mu upon sigma square, where minus infinity is less than mu is less than infinity and sigma is greater than 0, minus infinity is less than x is less than infinity, and e and pi are two constants. The main properties of the normal distribution curve are this being a probability density function, fx is greater than equal to 0, and area under the curve is 1, that is integral of minus infinity to infinity fx into dx is equal to integral of minus infinity to infinity into 1 upon sigma square root of 2 pi into e raised to power minus 1 upon 2 x minus mu divided by sigma whole square into dx is equal to 1. It is a bell-shaped curve and is symmetrical about its mean value mu. This implies the area on both sides of mu is 0.5, that is px is greater than equal to mu is equal to px less than equal to mu is equal to 0.5. The three measures of the central tendency, mean, median and mode are equal. The curve attains its maximum value at x is equal to mu. The point of inflection of the curve occurs at mu plus minus 1 sigma. The random variable x has an infinite range, that is, it ranges from minus infinity to infinity. The curve has asymptotic tails on the both sides that never touch the x-axis. Empirically, it is observed that the approximate percentage area covered between the limits mu plus minus 1 sigma is 68.27 and that of between mu plus minus 2 sigma and mu plus minus 3 sigma is 95.45 and 99.73 respectively. This can be observed from figure 1. The expression used to abbreviate that x is normally distributed with mean mu and variance sigma square is x ranges to n, mu and sigma square, where Ex is equal to mu and Vx is equal to sigma square. The two parameters of the distribution are its mean, that is mu, and variance or standard deviation, sigma square or sigma. Here mu is the center of the distribution and sigma explains the spread of values around the center. For every combination of mu and sigma square, a different normal probability curve is generated. As we can see in figure 2, distributions x0 and x2 have same means, that is mu 0 is equal to mu 2. But different standard deviations, whereas distributions x1 and x2 have some standard deviations, sigma 1 is equal to sigma 2, but different means. Furthermore, comparing distributions x0 and x1 have different standard deviations as well as means. All these distributions are termed as non-standard normal distributions. Need for Z distribution. If we are given that x ranges to n mu sigma square and probability that x lies between two numbers, that is a and b, is to be computed, then we need to integrate the function probability of a less than equal to x is less than equal to b, which would be equal to the integral from a to b 1 upon sigma square root of 2 pi into e raised to power minus 1 upon 2 x minus mu upon sigma whole square into dx. Since the expression in equation 2 is computationally very tedious, a set of tables is provided to calculate the probabilities. However, knowing that there can be infinite combinations of parameters mu and sigma square, and for each possible combination we would require a different table to calculate the requisite probabilities. We understand that this is practically not possible. The way out is that each normally distributed random variable is converted into a standard normal random variable called the Z variable. This standardized variable is used to calculate the probabilities of all normal distributions irrespective of the values of mu and sigma square. Transformation of normal to Z distribution and its definition. The transformation formula used is given by the expression Z is equal to x minus mu divided by sigma. That is, mu, the mean of x, is subtracted from the value of the random variable x, and this difference is divided by the standard deviation of x, that is sigma. Now the values of the two parameters of Z, the mean and standard deviation of 0 and 1 respectively. Ez is equal to E x minus mu upon sigma is equal to Ex minus mu upon sigma is equal to mu minus mu upon sigma is equal to 0 using the rules of expectations. Vz is equal to V x minus mu upon sigma is equal to Vx upon sigma square is equal to sigma square upon sigma square is equal to 1. So the normal distribution with its mean mu equal to 0 and standard deviation sigma equal to 1 is called the standard normal distribution, with the corresponding normal random variable being the standard normal random variable. Now using the standard normal variable Z, the equation 1 can be rewritten as Fz is equal to Fz 01 is equal to 1 upon 2 pi square root into e raised to power minus 1 upon 2 z square, where the z ranges from minus infinity to infinity and e and pi are two constants. The figure 3 here shows how every x variable with given mean and standard deviation can be converted into z variable. For example, let x tends to n, 4 and 1, the value of x is equal to 4 is transformed to z is equal to 4 minus 4 upon 1 is equal to 0. Similarly, the values x is equal to 3, x is equal to 5 are converted on z scale to minus 1 and plus 1 respectively. Properties of z distribution. All the properties of normal distribution referred above are same as that for the standard normal distribution or z distribution. However, we would rewrite few of them to clearly bring out the difference between the normal distribution and the standard normal distribution. The random variable z has an infinite range, that is, it ranges from minus infinity to infinity. the standard normal curve or Z curve is centered at its mean value 0 and is symmetrical around it, that is, area on both sides of the mean is 0.5. The probability of Z, which ranges from minus infinity to 0, is equal to probability of Z which ranges from 0 to infinity, which is equal to 0.5. Its point of inflection occurs at plus minus 1. Here you should notice that for normal distribution it occurs at mu plus minus 1 sigma. For Z curve, mu is equal to 0 and sigma is equal to 1. Therefore, 0 plus minus 1 into 1 is equal to plus minus 1. The cumulative distribution function of Z, phi Z, is equal to P Z less than equal to the small z is equal to the integral which ranges from minus infinity to z fy01 dy. The respective limits covering 68.27%, 95.45% and 99.73% of area under the standard normal distribution are given by plus minus 1, plus minus 2 and plus minus 3. Probability of z, which ranges from minus 1 to 1, is equal to 0.6827 is equal to 2p 0 less than equal to z less than equal to 1 is equal to 2 into 0.34135 into p minus 2 less than equal to z less than equal to 2 is equal to 0.9545 is equal to 2p 0 is less than equal to z less than equal to 2 is equal to 2 into 0.47725. P minus 3 less than equal to z less than 3 is equal to 0.9973 is equal to 2p 0 less than equal to z less than equal to 2 is equal to 2 into 0.49865. How to determine the standard normal probabilities or area under the Z curve? In order to determine the probabilities or area under the Z distribution, we use table A.1 titled Standard Normal Curve Area, attached at the end of this module. This table tabulates area under the standard normal curve that it lies to the left of a given value of Z, which can be observed from figure 4, written as Pz less than equal to small z is equal to phi z. Using this table, we can calculate the area under the standard normal curve lying between the two values of z and also above or below a particular value of z. This table provides areas for the values of z up to 2 decimal points. The first column of the table gives value of z up to 1 decimal and the second decimal point values are given in the topmost row, which are to be added to obtain the probability below a particular value of z. Though the curve extends indefinitely in both directions, the table provides values of z ranging from minus 3.49 up to plus 3.49. This range covers 99.96% of the total area under the curve. Here is an example. Find the probability of z less than equal to 1.32, probability of z greater than equal to 1.22, probability of z where it ranges from 0.58 to 1.62 and probability of z where it ranges from minus 0.38 to minus 1.12. The solution: probability of z less than equal to 1.32 is equal to phi 1.32. Now the value of 1.32 can be written as 1.3 plus 0.0. So the probability is to be seen in the table at the intersection of the row marked 1.3 and the column marked 0.02. From the table we see this probability is 0.9066. This gives the total area covered under the area between minus infinity to 1.32. See figure 5 over here. Probability of z greater than equal to 1.22. This requires computation of upper tailed area and this cannot be directly seen from the table as the table provides lower tail probabilities. Therefore, to obtain this we subtract the probability of z less than equal to 1.22 from 1. The intersection of the row marked 1.20 and the column corresponding to 0.02 gives 0.888. So the probability of z greater than equal to 1.22 is equal to 1 minus the probability of z less than equal to 1.22 is equal to 1 minus 1.22, which is equal to 1 minus 0.8888 is equal to 0.1112. Also, since it is a symmetrical curve, probability of z greater than equal to 1.22 is equal to the probability of z less than equal to minus 1.22, that is the area to the right of 1.22 is same as the area to the left of minus 1.22. The intersection of minus 1.2th row and 0.2th column in the table gives 0.1112, which is the same as obtained above. Probability of z, which ranges from 0.58 to 1.62, is equal to phi 1.62 minus phi 0.58, which is equal to 0.9474 minus 0.7190 is equal to 0.2284. Similarly, the probability of z, which ranges from minus 1.1 to minus 0.64, is equal to phi minus 0.64 minus phi minus 1.12 is equal to 0.2611 minus 0.1314 is equal to 0.1297. How to determine the percentiles of standard normal distribution? As we know, percentiles are the positional averages. These are number that divide the given data in 100 equal parts. For example, 67th percentile is the number below which 67% of the observations lie, and above which the rest 33% of the observations lie. In terms of the standard normal distribution, this can be interpreted as that value on the horizontal axis, areas to the left of which is 0.6700 and to the right is 0.3300. This can be observed from figure 7. So, the problem is being put in reverse fashion. Earlier we were given the value of z, and from the body of the table we had to find the probability. But now we are given the probability and the corresponding value of z is to be found. So, the table is used in inverse way. For this, we have to find that particular row and column, the intersection of which gives the value 0.6700. From the table, we find the probability 0.6700 corresponds to the intersection of 0.4th row and 0.04th column. This implies the value of z corresponding to 67th percentile is 0.44, that is 0.4 plus 0.04. By symmetry, we can say the 33rd percentile is when z is equal to minus 0.44. 33% of the observations lie below minus 0.44 and the rest fall above it. If probability of z less than equal to 0.44 is equal to 0.6700 is equal to phi 0.44 and probability of z greater than equal to 0.44 is equal to 1 minus 0.6700 is equal to 0.3300. Then symmetry implies that probability of z less than equal to minus 0.44 is equal to 0.3300 is equal to phi minus 0.44. Taking another example, to find 95th percentile, we need to find 0.9500 in the body of the table. Since this value does not exist in the table, we take the probability value which is nearest to it. Now from the table, we find there are two nearest numbers, 0.9495 and 0.9505, corresponding to z is equal to 1.64 and 1.65 respectively, which are equidistant from 0.9500. In such cases, we find the value of z by linearly interpolating the two values of z. Therefore, z is equal to 1.645 is the 95th percentile of the standard normal curve. By symmetry, minus 1.645 gives the 5th percentile. In inferential statistics, it is common to use z values that capture a specified area under the standard normal curve on either side of its tails. For example, Z10 denotes the value on the horizontal axis to the right of which 10% of the area lies. In general, we can say Z alpha denotes a particular value of Z that captures 100 alpha % of area under the Z curve to its right. For this, we can see figure 9. Further, this implies that the area to the left of Z alpha is 100 into 1 minus alpha %. Thus, by definition, we can say that Z alpha is the 100 1 minus alphath percentile of the standard normal distribution. By symmetry, minus Z alpha is the value that captures alpha area to its left. Z alpha is often referred to as the Z critical value in the hypothesis testing. Table 1 below gives the commonly used percentiles along with Z critical values required for inferential statistics. Table 1, percentiles of standard normal curve and Z critical values. Here we have the percentiles: 90th percentile, 97.5, then we have 99, 99.5 and 99.9. Then below each of these percentiles we have the tail area, that is alpha, then we have the Z alpha, that is a critical value, and minus Z alpha, the percentiles of the alpha. Note the numbers in parentheses give percentiles for the corresponding negative Z alpha critical value. Coming to the second example, find the following percentiles of the standard normal distribution. Also give the value of alpha in Z alpha, where alpha is the area captured to the right of the curve for each case, that is 90th and 25th. The solution here is the number closest to the 0.900 in the table is 0.8997, which corresponds to 1.2th row and 0.8th column. Therefore, the 90th percentile is 1.2 plus 0.08, which is equal to 1.28. The Z alpha is Z10 because the tail area to the right is 10%. The numbers closest to 0.2500 in the tables are the 0.2514 and 0.2483, which correspond to minus 0.77 and minus 0.78 respectively. Therefore, using linear interpolation, we can say the 25th percentile is approximately minus 0.775. The Z-day is Z 0.75 because the tail area to the right is 75%. Now the question is how to determine the area under non-standard normal distribution. If a random variable x is normally distributed with parameters mu and sigma square, then probabilities can be computed by standardizing the random variable x. Using transformation formula, we convert the x scale to z scale and the standard normal curve area table, which can be used to find the requisite probability. For example, if the probability is to be computed that x falls between two numbers x1 and x2, where x2 is greater than x1, then probability of x, which ranges from x1 to x2, is equal to probability of x1 minus mu divided by sigma less than equal to x minus mu divided by sigma is less than equal to x2 minus mu divided by sigma, which is equal to the probability of z, which ranges from x minus mu upon sigma to x2 minus mu upon sigma, which is equal to the probability of z less than x2 minus mu upon sigma minus probability of z less than x1 minus mu upon sigma, which is equal to phi x2 minus mu upon sigma minus phi x1 minus mu upon sigma, which is equal to probability of z less than small z2 minus probability of z less than small z1 is equal to phi z2 minus 5 z1. We know that the probability of x less than equal to small x1 is equal to 5 small x1 minus mu upon sigma, and probability of x greater than equal to small x2 is equal to 1 minus 5 small x1 minus mu upon sigma. Example 3. If x is a normal random variable with mu is equal to 6 and variance sigma square is equal to 25, find probability of x less than equal to 16, probability of x greater than equal to 1, probability of x which ranges from 5 to 11. The first is probability of x less than equal to 16 is equal to probability of z less than equal to x minus 6 upon 5 is equal to 16 minus 6 upon 5 is equal to probability of z less than equal to 2 is equal to 5 2 is equal to 0.9772. The second, the probability greater than equal to 1 is equal to probability of z greater than equal to x minus 6 upon 5 is equal to 1 minus 6 upon 5 is equal to probability of z greater than equal to minus 1 is equal to 1 minus probability of z less than equal to minus 1 is equal to 1 minus 5 minus 1 is equal to 1 minus 0.1587, which is equal to 0.8413, or this is equal to probability of z less than equal to 1, which is again equal to 0.8413 by symmetry. The third, probability of x which ranges from 5 to 11 is equal to probability of 5 minus 6 upon 5 less than equal to z less than equal to 13 minus 6 upon 5 is equal to probability of minus 0.2 less than equal to z less than equal to 1.4, which is equal to 5 1.4 minus 5 minus 0.2 is equal to 0.9192 minus 0.4207, which is equal to 0.4985. Other common applications of Z distribution. We have learned that any random variable that is normally distributed with given parameters mu and sigma square, it can be converted to standard normal variable Z to compute probabilities or area under the curve using the standard normal table. Now we will learn some other common applications of Z distribution. Many times we come across cases where the size of population is very large or infinite. It becomes cost ineffective in terms of time, money and effort to collect data from each object from the population. Instead, in such cases, data is collected from a subset of the population called sample. Based on the sample observations, we can calculate any quantity such as mean, standard deviation, trimmed mean and quartiles. Any such quantity whose values can be calculated from the sample observations is called statistic. A statistic is a random variable and has a probability sampling distribution because its value would vary from sample to sample. Further, how a sampling distribution of any particular statistic would look like depend inter alia on the distribution of the population from which the samples are taken. Sampling distribution of sampling means and sample totals. If the population under consideration is normally distributed on the basis of the results derived from sampling distribution of sample mean and sample totals, we can use standard normal variable to compute probabilities and areas under the sampling distributions. An important property of sampling distribution of the sample mean and sample totals is that if x1, x2, x3 up to xn be an independently drawn random sample of size n from a population that is normally distributed with a specified mean mu and standard deviation sigma, then irrespective of the size of n, the sample mean x bar is also normally distributed with population mean mu and standard deviation mu upon square root n. This means the sampling distribution of sample mean is centered at the population mean. However, it is less spread out than the population distribution. And the distribution of sample totals T0 is also normally distributed with mean n mu and standard deviation n into under root sigma. This suggests that sampling distribution of totals is centered at the population mean multiplied by the size of sample n, and it is more spread out than the population distribution. In terms of notations, it can be rewritten as x tends to n mu sigma square, then x bar which tends to n mu sigma cube upon n, that is E x bar is equal to mu V x bar is equal to sigma cube upon n, standard deviation of x bar is equal to sigma upon square root of n. Also T0 to n mu n sigma square, that is E T0 is equal to n mu V T0 is equal to minus n sigma square, standard deviation T0 is equal to sigma square root n. Using these properties of a sampling distribution, area under the curve between 2 points of x bar or of T0, that is the probability of x bar which ranges from A to B and the probability of T0 which ranges from C to D, can be computed by standardizing and using the Z distribution table. The formula for Z in case of the sampling distribution of the sample means is Z is equal to x bar minus E x bar divided by the standard deviation of x bar, which is equal to x minus mu divided by sigma divided by square root n, and that for the distribution of sample total is Z is equal to T0 minus E T0 divided by the standard deviation of T0 is equal to T0 minus n mu divided by sigma square root n. The weight of a certain kind of boards is normally distributed with mean 60 grams and standard deviation 10 grams. A sample of 20 boards is randomly selected. Find the probability that their average weight x bar is greater than 65 grams. Total weight T0 lies between 1431.5 and 1549.5 grams. Based on the properties of sampling distribution of sample means and sample totals, we know that x bar tends to n 60 100 divided by 25 is equal to x bar which tends to 64, and the T0 which tends to n 25 into 60, 25 into 100, or T0 which tends to n 1500 and 2500. Probability of x bar greater than equal to 65 is equal to probability of z greater than equal to 65 minus 60 upon 2, which is equal to the probability of z greater than equal to 2.5 equal to 1 minus probability of z less than equal to 2.5, which is equal to 1 minus phi 2.5, which is equal to 1 minus 0.9938, which is equal to 0.0062. Now looking at the probability of T0 which ranges from 1431.5 to 1549.5. This is equal to probability of T0 which ranges from 1431.5 minus 1500 divided by 50 to 1549.5 minus 1500 divided by 50. This is equal to the probability of Z which ranges from minus 1.37 to 0.99, which is equal to phi 0.99 minus phi minus 1.37, which is equal to 0.8389 minus 0.0853, which is equal to 0.7536. Generalization to sampling distribution of any linear combination. In the above subsection, we have talked about only two statistics, namely sample means and sample totals. In practice, we can generalize this result to any linear combination of sample observations. Let if x1, x2, x3 up to xn be an independent random sample of size n drawn from a population that is normally distributed with a specified mean mu and standard deviation sigma, and c1, c2, c3 up to cn are n numerical constants. Then y is equal to c1 x1 plus c2 x2 plus c3 x3 plus so on plus cn xn. That is, summation I is equal to 1 to n ci xi is a linear combination of xi's where ey is equal to c1 mu plus c2 mu plus c3 mu plus so on cn mu, which is equal to mu into summation I is equal to 1 to n ci, and Vy is equal to c1 square sigma square plus c2 square sigma square plus c3 square sigma square plus so on cn square sigma square, which is equal to sigma square summation I is equal to 1 to n ci square. Then y is also normally distributed with mean is equal to mu sigma I is equal to 1 to n Ci, and variance is equal to sigma square summation I is equal to 1 to n Ci square. In such cases, we can convert the random variable y into a standard normal variable to compute probabilities for y. Notice here, if C1 is equal to C2 is equal to C3, so on is equal to Cn is equal to 1, then y is equal to x1 plus x2 plus x3 so on plus xn is equal to t0 is equal to sample totals with mean is equal to mu summation I is equal to 1 to n Ci is equal to n mu, variance is equal to sigma square summation I is equal to 1 to n Ci square is equal to sigma square summation I is equal to 1 to n 1 square I is equal to n sigma square, and standard deviation of y is equal to sigma under root n. And if C1 is equal to C2 is equal to C3 and so on is equal to Cn is equal to 1 upon n, then y is equal to x bar is equal to sample mean with mean is equal to mu sigma I is equal to 1 to n Ci is equal to mu sigma I is equal to 1 to n 1 upon n is equal to mu into n upon n is equal to mu. Variance is equal to sigma square I is equal to 1 to n 1 upon ni square is equal to sigma square n upon n square is equal to sigma square upon n, and standard deviation of y is equal to sigma divided by under root n. So we understand from here that the sample means and the sample totals considered above in section 3.8.1 are two special cases of the linear combinations of sample observations. Here it must be kept in mind that the numerical constant c's can be negative numbers as well. If so, the expected value will change accordingly. However, variance will remain the same because in the formula square of c appears. Let xa, xb and xc stand for times required to carry out three different tasks at a different service station. Assuming these are independent random variables that are normally distributed with mean 80 and variance 49. Suppose a new random variable y is constructed where y is equal to xa plus 2xb minus 0.5 xc. Find the probability that y is greater than equal to 200 and the probability that 2y ranges from 408 to 420. The solution. In first case, in order to find this, we need to find Ey and Vy and then transform this into standard normal variable Ey is equal to Exa plus 2Exb minus 0.5 Exc, which is equal to 80 plus 2 into 80 minus 0.5 into 80 is equal to 200. And Vy is equal to Vxa plus 4Vxb plus 0.25 Vxc, which is equal to 49 plus 4 into 49 plus 0.25 into 49, which is equal to 257.25, and standard deviation of y is equal to 16.04. Therefore, the probability of y greater than equal to 220 is equal to probability of z greater than equal to 220 minus 200 divided by 16.04, which is equal to the probability of z greater than equal to 1.25 equal to 1 minus 5 1.25, which is equal to 0.1056. The second case, E2y is equal to 2Ey is equal to 400 and V2y is equal to 4Vy is equal to 64.16, and the standard deviation of 2y is equal to 8.01. The probability of y ranging from 410 to 420 would be equal to the probability of z, which ranges from 408 minus 400 divided by 8.01 to 420 minus 400 divided by 8.01, which is equal to probability of z, which ranges from 1 to 2.5, which is equal to 5 2.5 minus 5 1, which is equal to 0.9938 minus 0.8413, and this will be equal to 0.1525. Generalization to any linear combination with different population distribution. We could further extend this to even samples taken from different populations having different distributions as well as different means and variances. That is, making extensions to samples which are independent but not identically distributed. To keep it simpler, let us consider just two variables. If x1 and x2 are two independent random variables drawn from two different population distributions having mean values mu1 and mu2 and variances sigma 1 square and sigma 2 square respectively, and let y is equal to c1 x1 plus minus c2 x2, then ey is equal to c1 mu1 plus minus c2 mu2 and vy is equal to c1 square sigma 1 square plus c2 square sigma 2 square. Here it must be noticed that mean is not independent of change of origin and scale, whereas variance is independent of change of origin but not of scale. Therefore, whether the new variable is y is equal to c1 x1 plus c2 x2 or y is equal to c1 x1 minus c2 x2, the variance would remain the same. A chocolate manufacturer sells three varieties of chocolates: white x1, brown x2 and the dark brown x3. These are sold at Rs 4, 5 and 6 per bar respectively. Suppose the per day sale of all three varieties of chocolates in rupees is independent and normally distributed with mu1 is equal to 200, mu2 is equal to 350, mu3 is equal to 400, sigma 1 is equal to 40, sigma 2 is equal to 50, sigma 3 is equal to 60 respectively. Find the probability that revenue on a particular day from the sale of all three varieties exceeds Rs 5,000. Let the revenue from the sale is R, which is equal to 4x1 plus 5x2 plus 6x3. ER is equal to 4 mu1 plus 5 mu2 plus 6 mu3 is equal to 4 into 200 plus 5 into 350 plus 6 into 400 is equal to 4,950. VR is equal to 4 square into 40 square plus 5 square into 50 square plus 6 square into 60 square, which is equal to 25,600 plus 62,500 plus 1,29,600, which is equal to 2,17,700, and the standard deviation of R is equal to 466.6. Now the probability that R is greater than equal to 5,000 is equal to the probability of Z greater than equal to 5,500 minus 4,950 divided by 466.6, which is equal to the probability of Z greater than equal to 1.18 equal to 1 minus 5 1.18 equal to 1 minus 0.8810, which is equal to 0.1190. Normal density function is one of the most important and widely applied distributions in statistical theory. However, on account of its tedious calculations, we introduce a standard normal density function with mu is equal to 0 and sigma square is equal to 1, also called Z distribution. In this module, we have learnt how to transform normal distribution with any specified value of mean and variance to the standard distribution and thereby determine the area under the curve using the standard normal distribution table. Further, we learnt the common applications of Z distribution to the sampling distribution of sample means and sample totals.